what does that relate with the costume of your teacher today that he wears? What does that have to do with it? There's three words I want you to think about. One of them is called tolerance. The other one is accept. And the other one is embrace. What we say in the world is we must tolerate. This is not enough at all. Because the sword of Damocles in our head is waiting. So tolerance is not enough. If we don't have the soul power to embrace different cultures, different people, the way they live, the way they act, if we cannot embrace them and love them, at least we need to accept them. But tolerance is not enough in our days. Not at all enough. We need to forget the word tolerance. And if we don't have the soul power to embrace people with love, no matter who they are and what they're doing, then at least if we don't accept them, your generation and your children and my grandchildren are not going to have a happy days. This is a very serious message. And we might say, tolerate, but when we see people dressed in a different way, or they come from a different country, they speak a different language, even in the United States, that there is a lot of diversity, we still look people down. We say they are ignorant, they are, I don't want to say words. They are this, they are that. They have this religion, they have this nationality, and we put people down, thinking that we are better. That kind of attitude, as my students, I invite you to try the best you can to dissolve it, to kick it out. Then if you do that, you will say, I have done something really good during my college years. It will make you truly successful and happy. That is the message that your teacher is trying to tell you today by addressing his national custom, Cretan custom, native custom. And I see, I don't know how many other people did it, but if you have your custom today, come back here at the end of the lecture, and we're going to take a picture. And we're going to make this every review session, because the message is absolutely very important and very, we need to heed, to take into seriousness this message. Otherwise, there's no future for the world, we know that. And it doesn't matter what's going to happen, because I don't have control, you don't have control, what will happen tomorrow. But that which makes us happy, and everybody is going for happiness, is to do the right thing. Think, say, and do the right thing. Isn't that true? So I'll show you what we did yesterday at the gardens. Ready? Want to see? Let me show you. sons, there were 10 people in the gardens, they were in ecstasy. And they will do, I believe, much better than what they would do if they were worrying about it. So there's another type of reality. We live in a reality we create with our minds. The same moment that you're in your dormitory thinking about the world is chasing you to destroy you, there's other people that celebrate life. And the next day they have finals also. These 10 students, they do have finals too, like you. But they chose to purify their minds in nature with some other students and their teacher by singing beautiful songs and have a good time with campfire and so on and so forth. So, 5 minutes music. What happened? We were there from 3 o'clock to 9. If you think you're wasting 5, 10, 15 minutes a day because of this, your teacher trying to do it, it means the disease is very penetrating, all the way down to the stuff of the bones. And some people feel that way, they might leave. That's okay. Forgive them, love them, but if they happen to be your boss, without changing that kind of attitude, you better find a different job. Don't have these people as your boss. When it gets into that good stuff. Oh yeah. Don't forget these things that we talk about here. Don't allow the world taking the incredible beauty that you have inside you. Don't allow the world to do that to you. Okay, let's do this problem here. It's okay. If you see people criticize beauty, get mad at beauty, wherever they see beauty, don't bother with that. Because if you do, you also become darkness. There will be always people around us, but they will not love to see light. They will not love to see beauty. And they get upset with it. They will condemn it, no matter how beautiful it is. Don't be moved. As a wise person, do not be moved by it. Because if you are moved by it, then you become like that. Just completely ignore it. It doesn't matter who he is. Parent, brother, sister, roommate, schoolmate, teacher, it doesn't matter. Just ignore it. If you cannot embrace it and love it, at least ignore it. Don't be affected by it. Because then you lose all the beauty that you have in you. I guess your light is not on, huh? There you go. So this is the type of problem you want to find the rate law from experiments, right? That gives you the initial rate as a function of initial concentration, right? And sometimes it's easy to do these problems because you can see by choosing two experiments, right, from the table, if you see the concentration of one reactant remains the same, and the other one doubles, let's say, you see what happens to the initial rate. If it doubles, or if it becomes 4 times or 9 times, then you know the order on that species, right? But sometimes you can't. Sometimes you have to solve equations, algebraic system of three unknowns with 3 equations. This is an algebra problem, really, to find it, right? So, in this case, the way the numbers are, it's not easy to do it by just looking at it. Is that right? Because you can see the numbers are such that you cannot really, you don't have the concentration of one reactant in 2 experiments to be the same. Do you? No. So you really cannot do it by just looking at it. So there are some problems by just looking at it, you need to derive the rate law. You don't have to do any calculations. This problem is not such. This problem you have to do calculations, unfortunately. And so what do we do? Start doing it. Start doing it. And then we'll go together with it. Okay, so what we do is, we're going to assume, right? Can you hear me, you guys, or should I put batteries into my thing here? Can everybody hear me? Or should I change the batteries? So what do we do? What will be the rate law? How will it look like? Rate law, right, will look like, what are you going to, blue or red? Blue or red? What do you need? Doesn't matter, right? You can see it, right? So the rate law will be rate constant times 1. The reactants, but I don't know the order. That's what I want to find out. X and Y and K. All these 3 are unknowns to me. If I knew these values, right, then well, if I know X, Y, I know the order of the reaction, right? And then I might be able to find K too. Okay, so what do we do with that? Well, we go to the 3 experiments. If this rate law is for this reaction, that should be valid for every kind of experiment I do. Is that right? You change the different concentrations, right? Different initial rates. But every time the K has to be the same value, yes? So, for experiment 1, what are we going to have from experiment 1? It's going to be initial rate, it should be K, which we do not know, and the reactant concentrations are what? should be valid for any experiment, therefore for this experiment. And then from experiment 2, did exactly the same thing, 0.0922 is equal to K, you see, I'm going to tell you at the end of this lecture a lot of stuff that might help a lot for you for the exam. I know that some people left just because they were listening to these beautiful things that the teacher was telling today. They just got upset. They say, I came for chemistry. He's telling me about something else. I waste my time and my money. That attitude, some students do have it. And these students are not going to do as well, because I'm going to tell you things that they will be good for your exam. But they were not patient. They couldn't tolerate something. You see? So patience pays, always. If we are patient, we always pays us. If we are impatient, we always lose. Have you noticed that? I noticed that in my life. When I'm not patient, I always lose. I never win. Somehow, long term, short term, I'm going to lose. So it's good to cultivate patience, right? Okay, so did you write down for the second experiment? Right? And then from the third experiment, what are you going to have? Initial rate from the table. Right? So what you see now here, you have 3 equations with 3 unknowns. Now I'm not going to go how to solve this as an algebra problem. You should know how to do it. You can take logs, you can divide this by 2, this k goes away. Somehow you should know how to solve this problem, right? 3 unknowns, 3 equations, and then you, by doing this thing, you will find out that x is equal to 1, y is equal to 2, and k is equal to 1.25, molarity minus 2, second minus 1. And therefore the overall reaction order will be equal to what? 1 plus 2 is equal to 3. Yes? And the rate constant? We found it. Okay, then the problem is asking what's the rate of the reaction if you have this concentration. Well, big deal. You just apply the equation, right? So you just go from the rate law that you found now. Now you know the rate law. Right? Here is the rate law. And now you can find the rate because you know the rate constant is 125 and you have the concentration. And that's it. By doing the calculations, you will find out that it's 5.00. Molarity, second minus 1. That's it. Now there's a question. And the question is, could this reaction be one-step reaction? Explain. So what does the answer now has to be here? Is it the answer yes or no? How many people say yes? How many people say no? Just only 2 or 3. What's going on? Could this reaction be one-step reaction? Explain. If it was one-step reaction, what would be the rate law? Exactly what the coefficients are. You remember? We said that. And why? With the possibilities, remember collisions, you remember that? So if it was one-step reaction, then the rate law, I can see it by looking at the coefficients of the chemical equation. Is that right? So if it was one-step reaction, then what would be the rate law? If it was one-step reaction. The rate law would be rate equal to rate constant times what? A squared, is that right? Times B. If this was one-step reaction, this would be the rate law. Everybody agrees? Then, compare with experimental rate law. Is it the same? No. Therefore, this reaction could not be a one-step reaction. Correct? So the answer is no. The reaction, therefore, whatever it is a multi-step reaction. Okay? Let's go into another one now. Which one we're going to do? Let's see. How about let's do this one? This 38. Okay, let's do the 38 problem. Your teacher has been under many bosses during his career. Some of them, they were like monsters. Some of them, they were so kind and beautiful. And you had such a nice time with them. Doing your work pleasantly, keeping your family together. And the other ones, they almost got me divorced. They just squeezed and squeezed and squeezed, just killing you. And if you don't have the ability to master yourself, you might even get a divorce because of your boss. Do you know that? Yeah, because they might drive you crazy. They can ask you, you come on the weekends and the work or whatever. I want one result. I want this, I want that. And I was under that kind of people. And if you can avoid it, perhaps would be better. The best is to remain there and control your mind, your feelings, and be able to go through it, even with a monster in front of you. Just accept it, embrace it, and be powerful enough to go through it without even being bothered at all. That's the victory, yeah? If you don't have the power to do that, at least go before you go into the hospital, or to jail, or to the grave. Just go. Don't stay, go. If you want to practice and become stronger, stay. It's a good opportunity to become stronger. More patient, accepting, So try to draw it really fast. Okay? We've done that. Midterm 2, we had a similar one, right? I mean, first midterm, correct. First midterm, we had a similar one, right? So let's start doing it and let's do it together then. So it says, okay, so we have the equation, right? The redox equation that corresponds to a cell. You remember when, so we need to draw, right? Not the diagram. Here it says wrote the cell notation. That's a different thing. The diagram is the drawing. Okay. So we're going to have one. We're going to have one here, one there. Then we're going to have here a bridge. And here is going to be the membrane. So the solution will mix. Usually we put a potassium chloride salt here. Then we have an electrode here, an electrode there. Then we have a wire. It will look like this, right? Okay. So it tells us when you do this, make sure that you make these things. Make them so, and you cannot look on the down on the cathode. Okay. What is the anode and what is the cathode? Okay. The anode is always by definition goes to the left and where the oxidation also takes place, correct? So this is the anode and this is the cathode. And here is going to be oxidation and here is going to be reduction. Okay? These are by definition. There is no any mysticism into this. By definition, so we can communicate with one another in journals and the scientists and so on and so forth. They agreed and they said, we're going to put always the anode on the left and the cathode on the right. And by definition, at the anode, the oxidation is going to take place. Being electrolytic cell, galvanic cell or electrolytic cell, it doesn't matter. At the anode, oxidation, and the anode will be on the left and the cathode on the right. Okay, so far so good. Do you agree with that? Okay. So now we go here, and in the equation, what do we see? Which is oxidized? Tin from 0 goes to +2. Ah, tin is oxidized. That means it has to be in what? Left or right? Left. So, I have a solid metal. Yes, okay, well then this is going to be the electrode. It's going to be from what? Made? Tin. And what is going to be then the solution? Tin, anode, oxidized. Oxidized to what? Tin 2 plus. Okay, so it's Tin 2 plus, aqueous. Here, in solution, right? That's it. And how about on the other side? What's the electrode? What is reduced? Manganese is reduced from +7 to +2. So look at this, they're both ions. I don't have a solid. So when I have a solid, I'm going to use a platinum electrode, right? It's inert. So nothing will happen to it. So what I'm going to have here is, what I'm going to have here? I'm going to have the permanganate ions, aqueous. I don't have space to put it, should have been bigger, sorry. And then what else do you have? Manganese 2 plus, and what else? Don't forget the protons. Hydronium ions actually, right? All of them are aqueous. Sorry, I should have done it bigger, so you put all the species in that compartment there, right? So make it bigger if you have a problem like that in your exam. So the electrode is tin, platinum, anode, cathode. The ions are correct, all of them in there. Now we have to put down the direction in which the ions and cations migrate through the salt bridge. So here's the salt bridge. It's easier to do it by just remembering one thing, and then everything else is derived. Yes? So look how you will do it. Always remember, when you have a galvanic cell, at the anode where the oxidation is taking place, tin atoms are oxidized to tin 2 plus, and they just go into solution. Yes? Just like zinc with copper, you remember? And when they do that, the electrons remain here. Is that true? And because there is excess here, then they have to go through the wire. Why through the wire and through the water? I never really actually thought about it. Why they would go through the wire and not through the water? It's less resistant, really. So, now that they were oxidized and they forgot their electrons here, the cations jumped into the water, yes, the aqueous ion. This minus is not going to go like this, it's going to go like that because there is resistance. I never thought of that before. So the electrons are going to be moving like this. Do you agree with that? Okay, if the electrons are moving like this, look, like this, minus charge is moving like that. And the ions in the bridge should do the same thing. Do you agree with that? So the chlorides are going to go like this, and the cations, therefore, they will go the other way. This is, I think, the easiest way to do it, this kind of thinking, okay? There might be other ways to do it, but I think this makes sense. What do you think? Huh? I think it does. Okay. So we answered the A, and now it says write the anode half reaction. Okay? So how would you write the anode half reaction? Well, let's see. At the anode there's oxidation, right? So what is oxidized, we said? Tin. And where does it go? To tin 2 plus, aqueous. And that will give you 2 electrons, right? Because it talks about calculate E0, E standard, then you go on the back of your page of your exam and you look to find out standard. At this point anyway, even though the question is later, you can do it right now. You go on the last page of your exam, you find out that the actually reduction of tin 2 plus, because the table has what? Standard reduction. But you want here an oxidation, so you reverse it. Whatever you find on the back of your exam, you reverse it, the sign, right? So you find out that actually on the back of your exam is minus, but because it's oxidation here, no reduction, that's oxidation, reduction potentials. Now you have oxidation, you reverse it and you make it plus 0.14 volts. And then what else do you say? Okay, that's for A, BA. And then for B, write the cathode half reaction. Cathode means reduction. What is reduced? Permanganates. So you need to write down then the reduction of permanganate to what? To manganese 2 plus. So that will go to manganese 2 plus. aqueous. Now, you can balance it like the Chem 2A students do, or you can just copy from the back of your exam, because it's going to be in the back of your exam. You can copy it if you don't know how to balance it, because you can do it that way. And I'm not going to take time to balance it, because you're supposed to know really how to do this. But like I said, if you don't, it's on the back of your exam, so you just copy it there. And you look and you find out that the reduction potential of this half reaction is E standard plus 1.51 volts. Okay, great. So now it tells you to calculate the standard, E standard, right? That means the concentrations are all 1 molar. So you just add, right? You can add this, multiply by 5, by 2, and you have the overall balanced equation. You don't have to do it. It doesn't tell you unless it tells you to do it. And so E cell standard, because this is half cells, E cell standard will be the sum of this, the algebraic sum of this, is going to be plus 0.14 volts plus 1.51 volts is equal to plus 1.65. Notice what your teacher is doing. Always is using parentheses with plus in between, and always I put the sign no matter what, plus or minus. If you do that, you will never make a mistake. Right? Be consistent and be not sloppy. Parentheses, the signs always, and because we're talking about algebraic numbers, right? So you always should put the sign. It doesn't matter. If it's plus, put it. It's a good practice. Okay, and then we have the last thing to do is what? The cell notation. So let's do the cell notation. How would you do the cell notation? Okay, how do you start to do the cell notation? Okay, well, you say I have the bridge, and I have the anode, and I have the cathode. Yes? And when you have the anode, you have the electrode here, and then you have a solution here, then the bridge, and then something here, and then interface. You can have more than one line, actually, right? You can have 1 or 2, 3 lines, right? 1, 2 lines, right? And then you have the electrodes. So here's the electrodes, here's the solutions. You might have another one. You have to be careful. And here's the bridge. You agree with that? And on the left is what? The anode, where oxidation is taking place. From your reaction, what do you see? Tin is oxidized. Therefore, and we have tin solid, and therefore, since tin is oxidized, that's the anode, and the anode goes on the left, so tin is going to be here. Tin solid is going to be the electrode. And then we have the solution. What does the solution has? Tin 2 plus. So tin 2 plus aqueous is going to be here. Then we walk through the bridge, and as you walk through the bridge, you meet the solution first and then the electrode. So if that's the case, then you put down what? Whatever you have in solution. So what do you have in solution? Hydronium ions, aqueous, comma, permanganates, minus aqueous. Sorry, I should have made it bigger. Or I can put comma here and I'll put this on later. What else? Manganese, 2 plus aqueous. Then we have the interface. So there are 2 interfaces, and there is a bridge. And then what are you going to put? You look at the equation, you don't have a solid for the cathode. If you don't have a solid, then you put platinum. That's it. Done. Right? Any questions? Loud. You don't put the water. Never put the water. No, where are you going to put 3? We're going to put 3 there. Let me see. I had it 1, 2, 3, so we're going to get 3. But I have it taken with always 3. And put 3. Okay, so we have, I guess there's another class, so we have 10 more minutes. Yes. H plus or H3O is the same thing. Okay. So you don't put water, you never put water. Okay, we have 10 minutes left. So I'm going to have 7 minutes more actually, because I want to take a picture with one that has a costume. Because there's another class at 3. See, it's good I have the paper. Because sometimes they tell you go in there out. No, we have it by paper until 3. Okay. So let's do one more problem then. Let's see which one. Make sure you do A and B problems, yes? I mean, exam 1, exam 2, midterms, because there will be some of them really almost identical. Sometimes might be exactly the same, okay? That's okay. It's just called violence. That's called violence. But we react with beauty for violence, right? So don't worry about it. All right. So I think I'm going to do is I'm going to make sure that you know a few things I told you. I'm going to go over to make sure that you are aware of them. Just pay attention, right? If you really want to do a good grade, you will have to remember this instruction I'm going to give you before I close. So here is the instructions. Make sure you write them down or remember them. And like I said, the ones that they left, the human equations, they will lose a lot of things, I'm afraid so. Okay? Because that's the way it goes. No patience. Okay. Know the types of reactions. What type of, remember, isomerization, addition, all this. Know the difference, right? Between them. Here's in the reader. And then make sure there is problems in the reader with the square and vertical lines for what is the nuclear process. Positron emission, what is it? There's a lot of problems when you have a square, and then there is vertical lines and horizontal lines, right? You have an arrow going like this, like that, right? And the question is, what does it indicate, that diagram? You know what I'm talking about? So do these problems. Another one is in page 45, on page 291, the reader, 291, problem 45. Do that problem. There's a big molecule there. Do all the problems, all the questions there for that problem, okay? And then understand why aluminum chloride, for example, when you put in water, why it's acidic. Why aluminum 3 plus produces hydronium ions in water. Why it's acidic? Why it's acidic? Try to understand it, how it works, because by knowing it, then you will be able to answer the problem. And then there's two problems that actually I never put these problems before. So if you go to the Teaching Resources Center, they will not have it. Okay? It's very new problems. And I love it. It's beautiful problems. So I'm going to tell you to work it out in your minds, in your paper, ask the case to have the answers. Iron, actually, why if iron does not react with water, why do I have to paint iron structures? Prove it. Use equations, use numbers, your table, standard reduction potentials, use these things, just equations, and prove why, if iron is favored, actually, thermodynamically to be, if iron, thermodynamically does not want to react with water, right? Why then do we paint? So there will no rust. Why? One question, and that's explained. So it's quite a few points, maybe 10 points, I don't remember now. And there's another one, the other way around. If aluminum does thermodynamically has a tendency to react with water, aluminum does have thermodynamic driving force to react with water, why then we don't have to paint the aluminum surfaces of structures? We just leave them like that. We don't really paint them. They don't rust. They maintain themselves forever, practically speaking. So you can prove these two things very beautifully by using equations and a little bit of explanation, okay? And my friends, that's what I wanted to say today. I wish you good luck for all your classes. And if anyone has a costume, come and we'll take a picture with our costume. Okay, if anybody has a costume with himself.
pleasure.